In the final video today, I'm going to cover example 11.4 from the Dahm and Visco textbook. In laboratory experiments, the equilibrium pressure and liquid and vapor phase composition of the diisopropyl ether in 1-propanol system are measured at 303.15 Kelvin. The results are tabulated below, and we want to fit this data with both the 1-parameter and 2-parameter Margulies models. So this is our table of experimental data. As you can see, it goes from 0 to 1 for both X and Y, and it gives me the equilibrium pressure. First thing I'm going to do, which the textbook actually does not do, is plot this data. So I want to highlight, and I'm going to show you all of my steps and minimize the amount of skipping steps that I do, which may make it a little bit longer, but hopefully it'll be more informative. So the first thing I want to do is plot P versus X1. Because I've plotted it like this, I've actually inverted it. So I want pressure on the y-axis and mole fraction on the x-axis. So all I have to do is click on the data series, and then I can drag these things around. So the blue one is my y data, and the purple one is my x data. All right, so that looks like a pretty good dew point curve. Bubble point curve. Dew point curve. It is dew point curve. One of the two. All right, and I want to select data to get the other curve in. So I want to add and select x values. I want to plot y on the x-axis, and I want to plot P on the y-axis. Okay, and notice how I am plotting discrete data points because, and I'm not plotting a line through it, because when you have experimental data, recall that it is important to always plot it with experimental data points, because if you connect them with a line, that insinuates that you are modeling the data, which we are going to do. We will do that a little bit later on, but we want to plot just the experimental data points that we have. I'm going to pause to clean up this plot just to make it look a little bit more visually appealing. All right, so I've applied my usual modifications to my chart. Namely, I'm making the aspect ratio a square, and I can't do that because I can do it like this. Okay, so I've got a square aspect ratio. I've got darker axes, nice tick marks on the axes. I've done away with those sparse grid lines. Also done away with those orange and blue colors and replaced them by simple black squares. I've got a title for my plot, so now we know that this is a PXY diagram for the two components at 303.15 Kelvin, and I have labeled axes so that I know what I'm plotting versus what. So again, now what we're trying to do here is with the 1-parameter and 2-parameter Margulies models, we want to fit this experimental data such that we can figure out what the equilibrium compositions would be for any pressure. So first thing, order of business now is to calculate what the experimental activity coefficients are. So in another column, I'm going to make an experimental gamma 1 column and an experimental gamma 2 column. All right, and how do we calculate these? So recall that the modified Raoult's law is gamma 1 is equal to y1 times P divided by x1 times the vapor pressure. So first, I have to figure out what the vapor pressure is for both components at 303 Kelvin. This is going to require the use of the Antoine's equation to calculate what the vapor pressures are. So down here, I'm going to have a little section for vapor pressures and have diisopropyl ether and 1-propanol. And I need to look up what the Antoine's coefficients are. They are not in the back of a textbook. I've checked one textbook, so I'm going to go to NIST. So I'm going to stop share and share a Google Chrome window that I have open. Hopefully this is sharing now, but I'm at webbook.nist, and I have looked up diisopropyl ether, and I've got Antoine's coefficients listed there. So I'm just going to transcribe these A, B's, and C's into Excel. And I'm going to look up the same thing for 1-propanol, and notice something interesting. So I've got 3 separate entries here for the Antoine's coefficients. Which one should I use? The thought process here is that I know what my temperature is. So I know I'm at 303 Kelvin. So the third entry is out because this is for higher temperatures, the range of Kelvin is outside of 303 Kelvin. Now here, actually both of them are. So I have an easy decision. I have to use the middle one because that is the only one that encompasses 303 Kelvin. But say I didn't have that, you would be free to choose whichever one. So as long as your temperature range that is reported has that temperature of interest, I would go ahead and use those Antoine's coefficients. Pick and choose. It doesn't matter that the numbers are different, because as we've seen earlier, even if your Antoine's coefficients are all different than each other, they can all give you pretty good fits of your data. But again, once again here, I'm going to choose the middle one because that is the one that encompasses my temperature. Okay, back to Excel. I have to use the version of the Antoine's equation that is provided by the NIST webbook. So in NIST, I have the log base 10 version. So I have to do 10 to the power of the parameter A minus the parameter B divided by the temperature. And I'm going to $sign that one to copy the formula, plus C. And this is going to give me the answer in bar, I believe, and I have to close out the other parentheses. So Excel helped me out there. Yes, this is vapor pressure in bar. In order to use it, I need to convert my P star into kPa. I'll do that after I do the other Antoine's. So copy this down and double check that my formula references stayed constant. So I've got A, B, and C and temperature. That is correct. And now I need to look up the conversion between bar and kilopascals. And I think that one is 10 to the minus 2. Yeah, well, 10 to the 2 if you're converting this way. So I need to equals this and multiply by 100. Whoops. Multiply by 100 to get the answer into kilopascals. All right, perfect. Now I've got P star values for component 1 and component 2. Next, I'm going to calculate the experimental gamma. So like I said, I'm using modified Raoult's law, or the bread and butter equation, to say that the gamma is Y1 times the pressure, which is set by equilibrium. So these are going to be relative cell references, meaning no $signs, because I'm going to drag this all the way down. And divide that by, in parentheses, x1. And this is going to give me an error, which I fully recognize because I've got a 0 there and I can't divide by 0. Times the vapor pressure of component 1 in kilopascals. This one I am going to $sign because I want it to remain constant as I drag it down. And before I double check, I'm going to do the same equation for gamma 2. So equals Y1 times P divided by X1 times P2 star. All right, let me double check to make sure these are making sense. And I am noticing that I've got a few things that are deviating from the example in the book, and I just realized what they are. First of all, I should not have calculated the vapor pressure using Antoine's coefficients. I could have, right? But I should get that this activity coefficient goes to 1 when the mole fraction is 1, because that is ideal conditions. At a mole fraction of 1, I should have ideal. So this activity coefficient should be 1. And what the book is doing is you don't require Antoine's coefficient to figure out what the vapor pressure of the pure component is. I already know that the vapor pressure of pure component 1 for a mole fraction of 1 is 24.36. So actually I'm going to disregard this and backspace all of it and delete it. So delete, shifting cell, oops. Yeah, that's fine. I know why because I'm now referencing a cell that's not there. Instead of this vapor pressure, what I'm going to do is I know that the vapor pressure of component 1 is 24.36 kilopascals, as the experiment told me. Remember, experimental data is always more accurate than a model. And Antoine's equation is indeed a model. So I'm going to $sign that to keep it constant. I still have a divide by 0 because I'm dividing by 0 mole fraction. All right, that is much better. That's matching what I get in the book. And also I need to do the same thing for gamma 2. And the vapor pressure of pure component 2 is given when x1 is equal to 0. So I need to $sign that one. And then I also have to say that it's x2 and y2. Well, y2 for the top, x2 for the bottom. So I need to say 1 minus C6 here and 1 minus B6 here. And let's see, I need another parentheses. Perfect, that should be 1, and I should drag that all the way down, and I should get dividing by 0 error again. Perfect. All right, sorry about that mistake. So again, just use the pure component vapor pressures for figuring out what the vapor pressure is instead of Antoine's. Now I need a column for G, and I can't match the notation in the book, but this is going to be molar Gibbs energy excess divided by RT. And I'm going to calculate this one with an equation that I had in the last video, which is using the expression for a molar property as a weighted average of the partial molar properties. So I've got equals x1 times ln of gamma 1 plus x2, so that's 1 minus x1 times ln of gamma 2 equals. All right, got to divide by 0 again, that's okay, and I'll click and copy that all the way down. Beautiful. Okay, now I need to use solver. So in this, I'm going to break up the table a little bit because everything I've done so far is for the experimental. So now I'm going to model it with the 1 parameter Margulies. And I need a value for A. So I have to make an initial guess, and then I'm going to use solver to check myself. I don't know, what should we choose for A? Let's make it simple and say A is equal to 1. Should be about 1, maybe. We'll see what happens here. So now I'm going to have a GE over RT explained by the model, which is the 1 parameter Margulies, and I'm going to compare that but with the GE over RT experimental. All right, GE over RT for the 1 parameter Margulies is the parameter A times x1 times x2. So I want to $sign this one times x1 times 1 minus x1. Okay, not surprising I get a 0. But if I click and drag this all the way down, I am getting somewhat agreement. Okay, so my initial guess was not all that off. All right, I've still got some deviation from model and experiment. If I change the value of this A, I should get a different model result. So 2 is pretty far off. So I know that the answer is closer to 1 than it is to 2. So maybe I'll try 1.15. And oh, that's pretty close. Anyway, I could keep guessing and checking forever, but the only way to know for sure that I have a good result is to use solver. So I want to do something similar to minimizing the sum of squared errors. Now, I typically do the sum of squared errors. The book does something a little bit different. I want to try the sum of squared errors approach and see if I get good agreement to what the book says. So I want to also, I know what the final answer is here because I see what it is in the example in the textbook. So I'm going to go back and say that my initial guess was 1. And my SSE is going to be the difference between my model and my experiment squared. So we're going to have to throw out this first data point, obviously, because I've got to divide by 0. But if I do the rest of them, I should have some good errors. So I'm just going to delete this one and delete that one. And that's okay because I don't want, if I kept it in, I would mess up my analysis. So here I'm going to say this is the sum of all these squared residuals. They should all be positive, and they are. And now I want to set up solver. So this is under data again and solver. I want to set my objective, which is in cell I30, to be a minimum by changing the variable cell in the parameter A box. And I do not want to make unconstrained variables non-negative. I want to solve. And voila, I've got an A value of 1.164, which is exactly the same thing as the textbook examples had of 1.165. So this is the 1 parameter of the Margulies that I would see. Before I evaluate the fit, I want to go through and do the 2 parameter Margulies now. two parameter Margulies, and I'm going to need two parameters now. So I'm going to need an A. I'll put them over here. Or no, I can keep them. I'll keep them right below. A12, I'm going to give an initial guess of 1, and A21, I'm going to also give an initial guess of 1 and see what happens. So GE over RT model, in this case, is going to be not A times X1 times X2. Need to look it up. What is that model? X1 times X2 times the quantity of A21 times X1 plus A12 times X2. That was a bit of a mouthful. So equals, this is in your notes, by the way, X1 times 1 minus X1 times the quantity of A21. I'm going to $sign that one because I want that one to remain constant, times X1, and plus A2 $signed times X2, which is 1 minus X1. All right, hopefully I did not make a mistake in my parentheses. Let's see. That looks pretty good. Let's check it out. Perfect. Got it. And drag it all the way down. Have another column for SSE where I say the error is the model minus the experiment, or the experiment minus the model. That's the beauty of taking the square, is that it is indistinguishable which one you're subtracting. Copy it all the way down, delete these two data points, and say this is the sum of all of them. And I can run solver again to minimize the cell. This one is now L30. So I got to change that to L30, minimize by changing target cells of L4 and N4. All right, that's where my parameters are. Solve. Okay, let's see. How did I do? All right, pretty good. This one is a little bit of deviation from what the textbook has, but still pretty close. And again, I think it is because they are doing their sum of squared errors slightly differently. They have a little bit more complicated of a function. They call it OBJ. I'm not going to worry about it for now. I think sum of squared errors is going to be just fine for our purposes, and it gives an answer that's pretty close. All right, now the next thing to do is to figure out, or to evaluate how we did. So next I'm going to see if I can plot these lines with our model curves. All right, I've just cleaned up the Excel sheet a little bit to separate the one parameter Margulies model on the top, the two parameter Margulies model is going to be on the bottom. What we have to do is figure out an expression for gamma 1 model and gamma 2 model. And once again, this will allow us to plot as a function of x and y and do the dew point and the bubble point curves what the model should look like. So using the Margulies model, remember that ln of gamma 1 is equal to a times x2 squared. So to rearrange that, gamma 1 is equal to the exponent of the parameter a, which is going to be $, times x2 squared. So I need to do 1 minus x1 and square it. Highlight it all the way down. And nice, I've got pretty good agreement between gamma 1 of the model and experimental gamma 1. Next I need to do the same thing for gamma 2, and that is going to be exponent of the parameter a, $, times x1 squared. And copy that all the way down. Now notice that the activity coefficients, once again, are not constant with respect to composition. They are changing as I change my composition. Now that I have gamma 1 and gamma 2, I can do the dew point and the dew point curve and the bubble point curve. So I'm going to have two other columns for P dew and P bubble. And I'm going to calculate these how I did before for the Raoult's laws. All right, so the dew point curve I've shown before. I'm not going to go through the whole derivation. Go back and watch my video on plotting TXYs and PXYs using regular Routh's law if this confuses you, but I'll show you what the equation is. P, the dew point pressure, is 1 divided by, and there's a big term in the denominator, it's Y1 divided by the vapor pressure of component 1, which remember is given experimentally, which we know from experiment, times gamma 1. Make sure you've got your dollar signs where you need them and not where you don't need them. And I'm going to need some more parentheses here. So that's the first term. The second term is plus y2, which is 1 minus, 2 parentheses, 1 minus y1 divided by the vapor pressure of component 2 times the activity coefficient of 2. And being careful now to close out all my parentheses. Found a typo. That's almost never good news, but if you just accept what Excel thinks it should be, look, my dew point pressure that I've gotten by my model exactly matches what I get by experiment. So I'm going to click that formula all the way down and look at, I got very good, maybe not. Let's see, why did I get such big deviation here? I've got it. I told you to be careful with your dollar signs, and I was not careful with my dollar signs. I need to dollar sign A6. Let me hope that that works. Awesome, that's looking much better. Look at my agreement between my dew point pressure and the pressure that I get experimentally. So my column A matches very closely with column L. Going to do the bubble point curve before I plot them both. So the bubble point constraint is equals x1 times p1 star times gamma 1, dollar signs are in the right place, plus x2, so that's 1 minus x1, times vapor pressure of component 2, remembered my dollar sign that time, times gamma 2. That's looking good. All right, let's try to plot it and see how it looks. So I'm going to now select more data, and I'm going to overlay this. So I want to do series X values for my bubble point curve are going to be Y's, right? And my series Y values are my P's. Okay, and instead of modeling it like that, I want to format my data series. But let me see if I can change the chart type. I want a smooth line here. Oh, it's looking somewhat segmented and disjointed. So I know why this is. Remember that I am doing this for the exact data points that I have. But ideally, with a model, I should be doing many more data points. So what I should be doing is instead of only plotting for these data points, I should be starting at 0 for y1 and then going in regular intervals. I'm not going to show you that. I might do it afterwards and then show you what the final result is, but you should get a much smoother line than what I've shown here. But importantly, I want to show you that the fit looks decently good, especially for a 1-parameter Margulies. I would expect it to look a little bit worse than this. Let me just change that to a black line. You know what? Maybe a red line is typically how models are shown in literature. Notice that it's not perfect, so I've got a little bit of disagreement here, but in general, the model is giving me a pretty good fit for my data. Going to do the same thing with the dew point. So I want to select data, add the dew point. I need my X1s. And my series Y values are my P dews. All right, similar thing where it looks kind of sloppy and disjointed, but it's only because I've only chosen a few of the data points. But again, I got pretty good agreement up until the very end. All right, I think this video is getting a little bit long, so I'm going to, well, no, I'm going to keep showing you this. If you know all this, try and predict where I'm going to go next. So gamma 1 experimental and gamma 2 experimental. And for the 2-parameter Margulies, what is the model for the activity coefficients? This one is a little bit longer. So again, it is exponent. So I have to get rid of the ln by exponentiating both sides. It is x2 squared. So it is 1 minus x1 square times the quantity A12. Oh, this is going to be difficult. I got to make sure I don't make a mistake with this one because this one would be quite frustrating. 2 times A21 minus A12. Close out the parentheses and multiply by x1. Close out the other parentheses. Found a typo. Hopefully it works. Does my gamma match? Oh, I don't know yet. Okay, experimental gammas look pretty good. Did not make a mistake. Not yet, I don't think, at least. Gamma 2 is going to be exponent of x1 square times quantity of A21 $ plus 2 times A12 minus A21 times x2. Okay, maybe it wasn't so bad. 1 minus x1. Close, close. Use the color codings to see that my parentheses are all closing. All right, a 1 there is always a good sign. And do they match? My gamma 2s are not matching. Made a mistake. Rats. Let me troubleshoot it. Got it. Simple parentheses mistake. I need one less parenthesis there, and I need to close a parenthesis there. And why, I don't know why I did it in the middle. So I'm going to copy that all the way down. That looks good. Copy that all the way up. Now that looks good as well. Just a quick visual double check. And good. I've got a good match between my experimental gamma 2s and my model gamma 2s. You should say model, not experiment. Model. Okay, now I need to do the same thing. So maybe I should be able to just copy this formula. Let me see if I can do that. Because once I've got the gammas, it shouldn't matter much. Paste formula. And make sure that I'm referencing the correct cells. Okay, I think I am. Double click it all the way down. And same thing for P bubble. So copy and paste special. I don't know if I've shown you this before, but paste options, you have the option to paste a value or a formula. In this case, I want to paste the formula and then just double check and see that I'm referencing all the correct cells. So just to head off my columns appropriately, P do and P bubble. Okay. I'm going to plot these. Same exact steps. I'm just going to pause it and shorten the video a little bit. Okay, and I've finished that. As you can see, this model fits a little bit better than the one parameter Margulies does. So just looking at these data points here, they're much closely represented by this model. Overall, I've got a much better fit. It still looks somewhat segmented and a little bit cuspy because, again, I haven't chosen a smooth range of data. And I decided I'm not going to show you all of the data points. I think you understand what I'm talking about. And if not, we can talk about it on Monday. But again, the power of this is now that I've done this experiment, I can now plug in whatever number I want for a pressure. And I can use this model, or for an X and Y, I can use this model to figure out the vapor pressure, whichever pressure I want to know. So even though I didn't do the experiment for P is equal to 11 kPa, I would be able to use this without interpolation, because interpolation in general is not as accurate. And I would be able to figure out what the equilibrium liquid and vapor phases are. So take a look at the book if you have it. They did not do an analysis like this, but I think I chose to do this because I think it's the most accurate. They chose to evaluate their fit of model by looking at the activity coefficients and with the excess molar Gibbs free energy. But hopefully this gives you some valuable added perspective about what we mean when we say data modeling and why thermodynamics can be so powerful. That's all for today. Thanks for watching.